Alright, so now we are in chapter 7, oscillation and waves. Yeah, so this is a very long chapter. Okay, it has actually three parts. It has a simple harmonic motion, and then we have mechanical wave, and then we have sound wave. This one's application and Doppler effect. This one is under sound wave. Yeah, this one properties of wave and superposition of wave. This one is mechanical wave, and then this one is about simple harmonic motion. Okay, so simple harmonic motion, we will learn about the kinematics. Kinematics is about motion. Okay, motion, you know, when talk about kinematics, okay, when talk about kinematics, we talk about, you know, we have displacement, velocity, acceleration. Those are motion. Yeah, those are motion. Motion. Yeah. So we are going to talk about this, and then graph of simple harmonic motion, and then period of simple harmonic motion. Okay. First of all, I want you to remember that the simple harmonic motion is considered as just one particle. One particle oscillation. Later on, when we talk about property of wave, this one we have many particles. Many particles oscillation. This one is many particle oscillation. Yeah, so before we learn about many particle, we first learn about one particle oscillation. This one particle can be just the, like, for example, like the spring mesh system, just a one block, or the simple pendulum, just one pendulum. So this is like oscillation of one particle. Okay, so we are going to learn about displacement, velocity, acceleration of this simple harmonic motion. Yeah, and the graph and the period. So these are the learning outcomes that you need to know. Pay attention here. You need to know how to derive the equation for velocity, acceleration, kinetic energy, and potential energy, and so on. Yeah. So you need to know how to derive. So I will teach you how to derive. Okay, good. So now let's talk about what is actually simple harmonic motion. Okay, simple harmonic motion actually is a periodic motion. You know what is periodic? Yeah, periodic means you know, periodic means period lah. It has a certain period. It has certain period that is a back and forth motion, yeah, of an object about a fixed point called the equilibrium position. So it is a back and forth, means it's repeating. This motion is always excuse me, this motion is always repeat itself over and over again. Yeah, and the time for it to repeat is one period. Okay, like you see the simple pendulum. Just my animation lah. Let me show you my animation. Okay, see this is a repeating motion. Okay, it repeat itself. You see, this is called one oscillation. Okay, you see, it always repeat itself, isn't it? And then it has a certain period. Yeah, the time for it to complete one oscillation is always the same. Okay, the period is always constant. Do you notice that? The period is always constant. So the second time it repeat the motion, it also finish the motion with the same time. It finished the motion the second time or the third time with the same time. We call it the period. Understand? Okay, so it is a periodic motion. That means it always repeat itself, the motion, and the time to complete the motion is always the same, which is a period, we call it. Yeah, has a specific time. Okay, and then the back and forth motion about a fixed point called the equilibrium position. So it always oscillate around the equilibrium position. You know, okay, like you see here, it has an equilibrium position here, or this spring mesh system also, it goes up and down. It has a equilibrium position at the center. See, this one also oscillate. So always wait, I'm wrong. Actually, this is the equilibrium is over here. The equilibrium, let me write. The equilibrium is over here. I didn't see here. Position at rest. Equilibrium is here. Yeah. This ball also oscillate back and forth. So equilibrium is at the center. Equilibrium is at the center. Like that. Yeah. So this equilibrium position is a fixed point. Yeah. A fixed point where the things oscillate. Yeah. Just around this fixed point. So this is before that we have learned about linear motion, kan? Linear motion, and then we also learn about circular motion. We also learn about rotational motion. We already learn about how to find their displacement, velocity, acceleration. Even rotational motion also we learn about theta, omega, alpha, isn't it? So now in simple harmonic motion also it has their own kinematics, it has its own displacement, velocity, acceleration also, and some more they have their own equation. They have their own equation. Last time linear motion we have like equation v equal to u plus at, right? S equal to ut plus half at square. But what about this simple harmonic motion? What is their equation? What is the equation? Okay. What is the equation for displacement, velocity, acceleration in simple harmonic motion? So that's what we're going to learn today. Yeah. But before learning the equation, I have to discuss in detail what is actually simple harmonic motion first. Yeah. The definition of it. Now, example, for example, we have oscillation of block attached to a string, and then movement of child on a swing, motion of a pendulum, yeah, motion of the piston in the car engine, vibration of atoms in a solid. Okay, so see, all these are example lah. Okay, look at this one. Okay, so now we are entering the this topic. So now I want to explain what is actually simple harmonic motion. What is actually mean by simple harmonic motion? So this is about kinematics. Kinematics, that means about the motion lah. About the motion, yeah. That means we will talk about what? We will talk about kinematics is about the motion. It's about the motion. It's about displacement, velocity, acceleration. Yeah. So now. But for displacement, we have a term, we have a symbol for this chapter. The displacement we put as symbol y, yeah, y. But y is actually called position lah. Yeah, y is actually called position. Yeah, I will explain more about this later on. Yeah, I will explain more about this later on. Okay, now simple harmonic motion is a periodic motion without loss of energy. Okay, in which the acceleration of a body is directly proportional to its displacement for equilibrium position and is directed towards the equilibrium position but in opposite direction of the displacement. Do you understand this? Not really, never mind, because it's too long, right? Actually, this whole thing can be just summarized into this formula. Yeah, this is the formula to explain the whole thing here. Okay, explain the whole thing here. Okay, never mind. Let me explain one by one. Yeah. First of all, I want to wrap off all these first. Okay. Now, look one by one. Yeah. Look back one by one. The statement. SHM, simple harmonic motion, is defined as a periodic motion. That means it has certain. It always repeat itself with certain period. Yeah. Certain period, a fixed time. Okay, without loss of energy. You understand what is mean by without loss of energy? Can somebody tell me?
Energy is constant.
Energy is not lost. That means it always maintained in the form of mechanical energy. That means we can say no. The heat loss or energy loss due to friction is zero. That means no heat loss due to friction. And then that's why the system can oscillate forever. No damping. No damping. Okay, can oscillate forever. No damping happen. Understand? The energy is always the total energy always maintained in the form of potential energy and kinetic energy. The mechanical energy only. Only maintained in the mechanical energy. Okay, no heat loss due to friction. Look at my animation. I just love this animation that I made myself. Yeah. So you see, look at this animation. Yeah. Can you see it? Can you see it? So you see, this one. Okay. You see this oscillation happen forever. I've opened this animation for how long? Since the beginning of this lesson, but it still oscillate until now. Okay. Why? We can say because this this surface is smooth. Wait, let me see. Okay, I want to write something over here. So why? Because the surface is smooth. The surface is smooth. No energy loss due to friction. The surface is smooth. No energy loss due to friction. So the energy is always in the form of what? In the form of elastic potential energy. I should actually use a green, I should actually use a green elastic potential energy in the spring, or in the form of what? In the form of kinetic energy. Kinetic energy in the block. You see that? So that means the total energy. I want to write something. So the total energy is always in the form of the elastic potential energy in the spring plus the kinetic energy of the block, and it always constant. This is the thing, yeah. I want you to actually, I'm teaching the whole chapter, yeah. I'm teaching the whole chapter right from the beginning. You know that? Give you the concept. Actually, that's the important concept. The total energy is always constant. Can anybody tell me why? Okay. Maybe I'm getting too excited, yeah, seeing my animation. So I need to cool down for a while. Okay, so it's always constant, in the form of mechanical energy. In the form of mechanical energy of the whole system. When we talk about mechanical energy of the whole system, the system include what? Include the block, and also what? And also the spring. The whole thing here is one system. How to draw? This whole thing is one system. You understand? Okay. This whole thing is one system. So So this is in the spring. And this is the kinetic energy in the block. Understand? Okay. You see, look at which location it has the most elastic potential energy during the maximum compression or maximum. This is maximum extension, maximum compression. It has the most elastic potential energy, right? When do the block has the most kinetic energy? When do the block has the most kinetic energy? At the equilibrium position. At the equilibrium position, it has the most kinetic energy. You see that? You see, this energy always interchange from block to spring, spring to block, block to spring, spring to block as the block oscillate. I just love how this animation works. Okay, I just love how this animation works. I have the dreams of making this animation since I'm a kid, and today I success. Okay, so this is the thing I'm proud a bit lah. Yeah, okay. So Never mind, you just bear with me. All right. Okay. This is the the total energy of the whole system is in the form of mechanical energy, and it always constant. Why it always constant? Because the surface is smooth, no energy loss. You understand? You understand now? Can anybody give me some response?
Yes, sir.
Yes, sir.
Okay, very good. Thank you very much for your response. Just keep it for a while. The annotation is still there. Okay, let's go back. You see, now you understand the statement here. Periodic motion without loss of energy. Because that's why it can oscillate forever, no damping. The animation is still. Oh, sorry. The animation is still carry on until now. Yeah, no damping at all. Doesn't slow down. Sorry, doesn't slow down and always carry on forever. Okay, I should continue. Now, in which the acceleration of a body is directly proportional to its displacement. What does it mean by here? Acceleration of a body is directly proportional to displacement from equilibrium. Directly proportional. What does it mean? You look at here, yeah. So I want you to. This is one statement. Acceleration proportional to what? Displacement from equilibrium. Okay. So this statement. Acceleration proportional to displacement. So how is it? How do you understand this? So you can actually just write it like you can write it in this form. Okay, you can write it in this form. Am I still? Let me change the color for a while. Okay, still red is better. So acceleration is proportional to displacement. Displacement we put as y, yeah, symbol y. There's a reason why we use y. Okay, acceleration proportional to displacement. Okay, that means what? That means if let's say the displacement increase, acceleration also increase. They also increase. So if displacement zero, acceleration also zero. Okay, if displacement is zero, acceleration also zero. If displacement increase, acceleration also increase. Look at my animation. I just use my animation. So okay, I want to rub off the rest of things. I want to rub off. I cannot rub off anymore. Oh gosh. Never mind. Just delete. And okay, never mind. It's okay. Okay, I want you to understand this. Okay, acceleration proportional to displacement. That means when displacement zero, acceleration zero. When displacement increase, acceleration increase. So is that true? Look at this animation. You see the blue line, the blue arrow is what? The blue arrow is the displacement. The red arrow is the acceleration. The orange one, the orange is velocity. Okay, so this is okay. Let me write it down. So this is this is a displacement. This is a velocity. This is acceleration. I want you to check. I want you first to check the the displacement and acceleration. Okay? I want you to check the blue arrow and red arrow. The blue arrow and the red arrow. And compare them. Compare. I want you to compare. You see? Actually, I can add one more function for this animation. A start-stop button, I can do that. I know how to do the start-stop button and play button. and forward button, backward button. Right now I haven't do the button yet. Okay, later I will add. But because I want to stop at certain moment, yes, for this animation to happen. So anyway, look carefully. You compare between the displacement and acceleration. What do you see? What do you see? When the blue line become zero, the red line also becomes zero, isn't it? Correct or not?
Yes, sir.
When the blue line increase in length, the red line also increase in length. You see that? See or not? When the blue line become longer, red line also become longer. Do you see that?
Yes.
This is what I mean. This one, and some more. You see, they are opposite direction all the time. You see that? They are always opposite direction all the time. They're always opposite direction all the time. Acceleration and displacement always opposite direction all the time. Okay? And one more thing. Look at the acceleration. Look at the acceleration. It always point towards what? What direction? The acceleration always point toward what direction? The acceleration always point... Huh?
Equilibrium.
Equilibrium! Good. You know, I clap my hand now. Okay? So you see the acceleration also always point towards equilibrium. That's correct. You get the whole meaning already. So first thing, I want you to write it down. What's the first thing you encounter? Okay. What is the first thing you encounter? First thing you notice that acceleration is proportional to displacement. That means you know what? That means when displacement increase, acceleration increase. And then another thing is what you notice. The second thing you notice is acceleration always opposite. Alamak. Wait a second. Acceleration always opposite displacement. Correct or not? Always opposite direction. The third thing you can see, acceleration always towards what? Towards what? Equilibrium. The direction. Okay, so this is the meaning of SHM. This is the meaning of SHM, the definition. Okay, so let me keep it. Okay, so this is the thing you notice. Acceleration always opposite the displacement. Now I want you to look back to the definition again. I want you to look back to the definition. Put it side by side like this. Isn't it amazing? Okay. How computer works, yeah. So put it like this. You can see clearer now, yeah. So you see now, can you understand about this? Can you understand? Acceleration of a body is directly proportional to displacement. Acceleration proportional to displacement. Is that what you see? Acceleration directly proportional to displacement. So that's the first thing you see, isn't it? And then secondly, what you say again? What's the second thing you say? Look at here. Acceleration is directed towards what? Towards what? Equilibrium. Fantastic. Yeah, I can say you are fantastic. It always directed towards equilibrium. So that's the third thing you see. Acceleration always towards equilibrium. And then what's the third thing? But what? But
opposite direction.
Baguslah. Ya. Apa lagi boleh saya kata? You bagus. Ya. That means that acceleration is opposite direction of displacement. Acceleration is always opposite the displacement. Acceleration always opposite the y. Y is the displacement lah. So acceleration always opposite direction to the displacement. Now do you understand the whole statement here?
Yes, sir.
Bagus. Baguslah, bagus. Apa saya boleh cakap? Bagus saja. So you see that acceleration always opposite displacement. Okay, but some of you may ask, why is it why is it displacement must to the right and then to the left, to the right like this? Do you know why? This one need to explain deeper. Why displacement? Here displacement to the left, why here displacement to the right? This is the meaning of displacement, right? If the block, look at here, if the block at the right hand side, that means displacement here, if at the block at the right hand side, displacement is positive. I put as y lah. Should use y. Put as, I mean y is positive, isn't it? If block is at the right hand side of the equilibrium, at the center is equilibrium. That means displacement zero. Displacement zero. If the block is at the equilibrium, displacement is zero. So if the block is at the right hand side, then the displacement is positive. If the block is at the left hand side,
Negative, sir. Negative.
Negative. So displacement is negative. Oh, it's too. Displacement is negative. Alamak. Yeah, too many animation also. Kacau So okay. So displacement negative, displacement positive. Boleh faham displacement? Boleh, bagus lah. Sometimes we can write, displacement. Here we can write displacement equal to positive 10 meter. Yeah, maybe 10 meter is the amplitude. Here we can write displacement equal to negative 10 meter like that. Yeah, we can write it like this. Never mind. Okay, so I can write on my animation some more. Okay, look at this red line. Now, red line, some of you may ask, why acceleration always towards equilibrium? Why acceleration always towards equilibrium? This one you must ask the force. You must ask the force in the spring. The force is the spring that causes the direction of acceleration, because the force in the spring always tends to pull or push back to the equilibrium position. So acceleration follow the direction. Okay, this one we will talk about direction of acceleration later on. Yeah. But I just want you to see only. You see, when displacement zero, what is acceleration? What is acceleration? When displacement zero, acceleration zero. See, acceleration also zero. Correct or not? Correct. Yeah. Okay. Very good. Very good. Okay. Look at here. Look at this arrow line. No, red line. You see, if displacement is positive, what is the acceleration? Acceleration is negative. Correct or not? Because to the left. Acceleration is to the negative. And when the displacement is negative, what is acceleration? Acceleration is to the right. Correct or not? Acceleration is to the right. So acceleration positive. See that? The opposite direction. Okay. Okay. Now I want you to look at the. Okay, keep it. Yeah. So look at the notes here. So this whole thing actually can be summarized in this equation. So this equation actually explains the whole thing here. You see, look at this one. I want you to you see, when displacement increase, acceleration increase, they are directly proportional. You see that? The acceleration directly proportional to displacement, already explained. And then some more, the negative sign. The negative sign means what? What is mean by the negative sign? What is mean by the negative sign? The negative sign shows that acceleration opposite to displacement. Understand or not? So just like the animation just now, you see, look at this one. Look at this one. See, when displacement positive, acceleration negative, correct or not? So if you look at here, if I put here acceleration positive, okay? No, I mean displacement positive. So positive multiply negative, you get what? Acceleration negative, correct or not?
Yes.
And if displacement is negative, what is acceleration? Acceleration positive, correct or not?
Positive.
As displacement negative. Is displacement negative. So negative multiply negative, you get
Positive.
positive. Actually you speak to me, actually help yourself to understand more, you know that? Because the words come from your own mouth. The words come from your own mouth. You're actually teaching yourself. You're actually teaching yourself. You are telling yourself. So that's why I need you to respond. You respond actually means you are teaching yourself. If you don't respond, means you are not teaching yourself. You are not telling yourself. And you don't remember, you don't understand. And that's why I need you to respond. That's the reason. Understand or not? Yeah. I can do all the talking here. I can do all the talking here. Yeah. But the word doesn't come from you. The word comes from me. So I don't know whether the word enter your head or not. But if the word come from your own mouth, you're actually teaching yourself, telling yourself stuff. You are making yourself understand more. Yeah. Okay. Never mind. Skip all this nonsense. Okay. So, okay, you understand that? So this negative sign, what does it mean? What does it mean by this negative sign? What does it mean by this negative sign?
Direction of
Opposite direction.
Acceleration is opposite direction to the displacement. Yeah, that's what it means. Yeah, when positive, negative, 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 positive. That is what it means lah. Become opposite direction, but they are proportional. So you see, this one simple formula explain the whole SHM definition. So I can actually say this equation is the SHM definition. This is the SHM definition. Okay? Baik. Now, let's continue. Omega is actually angular frequency. Omega is, this thing has their own period, right or not? It has their own period. So, omega, we can find a period. Do you know that? Never mind. Now you know. So, omega is 2 pi over period. So this omega value can help us to get the period of this oscillation. You know the period you get from your stopwatch in the experiment. Yeah, you calculate the time for 10 oscillation, and then the time you divide by 10. That's the period. So that's a period. That's a period here. That's a period here. You use 2 pi divide by the period you measure from your experiment. 2 pi divided by period, you get the omega. And you get the omega, you can put into the equation. You get the SHM equation for your simple pendulum oscillation. Do you know that? So,
yes.
that oscillation can be represented by one equation. Okay, enough talking of this, this thing lah. Okay, so example. Now here, example of simple harmonic motion. So we have several example here. We have, simple pendulum. We have a frictionless horizontal spring oscillation, and then we have vertical spring oscillation here. Now, some of you may ask, why acceleration is towards equilibrium? Why? Look at again my animation. Yeah. Why the acceleration always towards equilibrium? Why acceleration always towards equilibrium? Why? I told you it's about the spring, the force in the spring. You see, when this spring is being extended, what do you think the spring will do? When the spring is being extended, let's say the block is over here. When the spring is being extended, what do you think the spring will do? What do you think the spring will do?
Dia tarik balik ke
Tarik balik, betul. Tarik balik. Pandailah. So dia nak tarik balik. Spring itu dia nak tarik balik. Spring nak tarik balik. Spring, kan? So we can say actually this is the force in the spring is what we call restoring force. It's the restoring force. That means restore what? Restore it back to equilibrium. lama-lama tengok animasi ni, you lama-lama jadi faham, bukan jadi mengantuk jadi faham. So ni spring nak tarik balik ke equilibrium, betul tak? Kalau spring kena compress, macam mana? Kena compress. Kalau you ditindas, you buat apa? You biar dia diri ditindas lagi, atau you buat apa? Kalau you ditindas, you di-oppress, apa you buat?
Tolak balik.
Tolak balik, betul. Saya bukan ajar benda yang apa di sini. Saya cuma kaitkan dengan real life saja. Okay, so this is a tolak balik lah, betul tak? We have fighting spirit, isn't it? Dia tolak balik. So force in the spring dia apa? Tolak balik. Kenapa nak tolak balik? Sebab nak kembali normal, kan? Nak kembali normal. Ya, nak kembali ke equilibrium. Nak block ini kembali ke equilibrium, kan? Spring kena tolak balik. So itu sebabnya acceleration follow the force in the spring. Because apa? Because of Newton's second law. Yeah, because of Newton's second law. You know, this is a total F equal to ma. You understand? Total. So what is the force acting on the block? What is the force acting on the block? What's the force acting on the block? No friction. I say already, this surface is smooth, kan? Smooth. And then the weight and the normal force being cancelled off. So the only force acting on the block is only the force in the spring. Betul. Ayah. You faham tak apa saya cakap ni? Maksud baguslah. Macam itulah, kan? Kalau macam let's say spring is being extend, in equilibrium, spring kena extend, kena extend ada y positif. So lukis dia punya free body diagram. Saya nak kamu lukis free body diagram. Lukis free body diagram. So dia ada weight, kan? Betul tak? Dia ada weight, dia ada normal force, kan? Betul? Tapi itu kita tak kisah, kan? Kenapa tak kisah? Sebab dia cancel off, betul tak? Lagi satu ini smooth, kan? No loss of energy, kan? Betul tak? No loss of energy means no ataupun friction is zero, kan? Betul tak? So apa force yang bertindak atas dia lagi dalam X component? Dalam X component apa force lagi? Dia kena tarik. Spring ini kena tarik. Block ini sudah tarik, dia ada positive displacement, ada extension sudah. Apa dia buat? Spring apa spring buat sekarang? Kalau kena tarik, dia apa buat? For spring force in the spring je lah, betul tak? Yang bertindak atas X component, betul tak?
Betul.
Kalau X component cuma ada force in the spring. So the resultant force is only force in the spring. Bagi normal force dan weight sudah cancel off, tak ada kaitan sudah. The Y component itu tak ada kaitan. Tak ada kaitan. Ya. Tapi dalam apa? Kita sudah belajar chapter 3, kan? Acceleration, kan? So sekarang resultant force ke arah kiri. So acceleration ke arah mana? Acceleration ke arah kiri. Alamak. Acceleration ke arah kenapa? Tak kena set. Acceleration pun ke arah kiri, faham tak? Kalau ada resultant force ke arah kiri, acceleration pun ke arah kiri, faham tak? So force in the spring, so resultant force on the block is only the force in the spring. So force in the spring ke arah kiri, so acceleration pun ke arah kiri. Kalau force in the spring ke arah kanan, force of spring ke arah kanan, acceleration pun ke arah kanan. Tengok tak? Ke arah kanan. So what I can say is force of the spring always towards equilibrium juga, betul tak? Betul tak? Force in the spring always towards equilibrium because he want to. Why always towards equilibrium? Because he want to restore. Because it's a restoring force. So acceleration pun ikutlah. Faham?
Faham.
Baguslah. Bagus. Saya bersyukur. Sebab you sudah faham. So sebab force in the spring is a restoring force. Always towards equilibrium. That's why acceleration also towards equilibrium. That's the only force acting on the block for the x-axis. Okay, bagus. Selesai. Keep it. Okay, and then, so you sudah faham spring. About ada 5 minit. I will finish this. Ini. How about ini? Wait. Ini kenapa dia restoring force datang dari mana? Kalau spring, kita tahu ada force in the spring kan? Kalau spring, kita tahu ada force in the spring. Kalau macam pendulum ini tak ada spring kan? Tak ada spring. So, macam mana dia nak balik ke equilibrium?
Gravitational acceleration.
Gravitational force. Baguslah. You sudah tengok video di YouTube saya kah? Bagus lah. Semua pun tahu. So, itulah dia. Ya. Begitulah cara ya kita kena prepare dulu supaya lebih faham. Betul, dia ada gravitational force. Mari kita lukis free body diagram dia. Ya, 5 minit ini. Ini ada weight dia kan. Ini ada weight dia, so dia ada. So, ini boleh resolve kepada komponen. Ya, boleh resolve kepada komponen. So, mari kita resolve. Kita resolve kepada begini. Ada sengit sikit dia punya axis. Y-axis dia ikut string dia. So ini adalah apa? Di sini adalah theta loh. Di sini adalah theta. Di sini adalah theta. Nampak tak? Corresponding angle. Here angle and here angle is the same. So this one can be resolved into two components. Do you know that? Now you know. Yeah? Now you know. Or you also already know. Yeah? If you really think hard, you can actually know by yourself. Okay, you see. So this weight got two components. It got x component and y component. This we can say this is the this is the x component and this is the y component. So what is the y component of the weight? What is the y component of the weight? Y component of the weight is w cosine theta. Understand? What is the x component? I use the red color. Red color looks nice to me. W cos theta. How about the x component? X component is W sine theta. Okay? W sine theta. So, can you see here? And then, in the string got what force? In the string here got what force?
Tension.
Tension. Bagus. Tension. So, you tahu tak? Sekarang you sudah tahu. Tengok ini. So ini y component. Kalau y component ada force lagi, y component sudah cancel, betul tak? Sudah cancel. Tinggal force apa?
W sin theta.
Ya, tinggal x component saja, betul tak? Tinggal x component saja. So this one is the resultant force. So kita boleh cakap macam ini, kita boleh tulis begini. So kalau dalam y component, susah ni pen ni, ya. Kalau dalam x component kita ada MA kan, MA. So yang force dia adalah W sin theta aja, betul tak? W sin theta aja yang equal to MA. Kalau total Fy ialah 0 sebab T dan W cos theta ni sudah cancel. So dia jadi kosong. So yang bagi acceleration ini ialah W sin theta. So dialah W sin theta inilah ialah apa? Restoring force. Fs. Fs actually is called restoring force. Restoring force. Understand? Equal to MA. So kalau dia punya dia punya A ke arah mana, dia punya force ke arah mana, A pun ke arah mana lah. So sekarang dia punya W sin theta ke arah mana? Dia punya W sin theta ke arah mana? Ke mana? Ke equilibrium, betul tak?
Ya.
Equilibrium. W sin theta ke equilibrium. So A dia pun ke equilibrium. Actually A ni kena tulis sengit sikit. So A pun ke arah equilibrium. Itu maksudnya. Faham tak? W sin theta ke arah equilibrium. So A pun ke arah equilibrium. Kalau dia punya let me see kalau where is it? Kalau pendulum di sini, macam mana? Kalau dia punya pendulum di sini, kau boleh bayang sendirilah kan? Bayang sendiri. So ini dia punya W di sini kan, betul tak? So dia punya theta di sini. So W sin theta ke arah kanan pula. So A pun ke arah kanan, betul tak? Always towards equilibrium. Itulah cerita dia. Tengok balik animasi saya. Dan itulah dia ya. Kenapa acceleration always towards equilibrium. Okay. So ini sahajalah untuk hari ini. Ya, nanti kita sambung lagi. Boleh faham semua?
Boleh.
Bagus. So nanti ini video saya akan post ke YouTube lah. Ya, you boleh tengok balik. Ya. So itu saja untuk hari ini. So kita jumpa lagi next week. Jangan lupa hari ini kena submit semua you punya tugas assignment yang chapter 6 itu rotational rigid body. Submit hari ini ya. Hari ini last. Kalau esok you submit, sudah tolak markah. Akan deduct mark for late submission. Okay. So check balik-balik. Pastikan ada free body diagram. Pastikan ada equation. Setiap explanation itu mesti ada equation to support. Especially question 1A. 1A itu mesti ada equation to support. And then itulah check you punya jawapan dengan kawan-kawan. Tengok betul tak, tally tak. Ya. Kalau tulisan buruk, sila tulis kemas sikit. Saya tambah ada tulisan yang buruk. Alright. Okay, so saja. Terima kasih. So see you next week. Bye. Jangan lupa ada UPS 2 untuk next Monday ya. UPS 2. So sila buat you punya objective question this weekend. Objective question for chapter 4, chapter 5, chapter 6 until chapter rotation ya. Work energy, circular motion and rotation. Prepare for UPS 2 next Monday. Okay, bye.
Okay,
thank you, sir.
Okay, sama-sama.